All right, notes. Good Lord, we'll get there eventually. This slide is called Vertical Stretches and Shrinks. We've saved stretching and shrinking for today. I've given you, yes, you guys should have learned this in algebra, you should have, but a lot of teachers don't focus on it in Algebra 1 because it's not really a big deal on the Algebra 1 FSA, so I don't blame them for that. Since it's not a big deal for their test, they don't put a whole lot of effort into it. I get that. Algebra 2 is not a graduation requirement. Nope. So what we have here is f of x equals the absolute value of x minus 2. I've given you its picture right here. It says find and graph 2 f of x. Now, we have seen a number in front of f of x before. We have. But it didn't look like a number. What you saw was a negative sign. But you have dealt with something sitting in front of f of x already. We did it last week. So you should know how to do it. It says put a 2 in front of your f of x. Now, in mathematics, anytime you stick a number in front of something, what you're being told to do is multiply. So you've been told to multiply the left side of the equation by 2. And we all know our algebra skills by now. If you multiply the left side by 2, you better multiply that right side by 2. But, class, how do I make sure I catch the whole right side? One person, class of 1, my man. Parentheses. You need parentheses. Need parentheses if you're going to capture the whole side. Last period I said you need parentheses because you got to catch them all. Not a single giggle, so I didn't make the joke this period, but I thought I'd tell you. So the 2 gets distributed to everything that's on the outside, including that number that sits in front of the absolute value bars. But Mr. M, there's no number there. Yes, there is. There's a 1. So we need to distribute the 2 to in front of the absolute value bars and to the number at the far right. We've been asked to call that g of x. Stick that 2 in front, absolute value of x minus 4. There, we have our equation. Woo. What we're going to do is we're going to graph it so that we can see what effect putting that 2 on the front had on the graph. So this gives us good review on how to make our point trees for our absolute values as well. Gives me a chance to talk about vertex, remembering that the vertex can always be found the exact same way. You tell me what number you'd have to plug into the inside to get a 0 on the inside. Lots of voices? 0. So if you plug in a 0, yeah, the inside now equals 0. And the y value of the vertex is always found the same way. It's the number to the far right. So for this one, it is -4. Ooh, oh, by the way, just putting it out there. See this -2? See where this thing is? At -2. Yeah, just demonstrating that I'm not full of baloney, that it's a true thing. Okay, shortcut that I taught you. If there's not a fraction in front of the absolute value bars, then you could just move my 1s. Go left 1 and go right 1. So -1 and +1. And you just plug one of those in to see what your y values are. It doesn't matter which one. I like to go to the right. I feel like that's the easy way. So you're going to drop a 1 where the x is, and then subtract 4. Well, 1's already positive, so that just says 2 times 1. And that gives you 2 minus 4, which is -2. The graphs are symmetric, so there's a -2 both here and here. Let's plot those things, and we're going to call that one G. 0, -4, 1, -2, and -1, -2. Connecting our dots to the best of our abilities. And this is G. So the very first week of school, we saw some graphs get transformed. And we were describing them very loose manners, verbiage that I was like is good enough for now. The red graph, does it appear to be more narrow than the black graph? Yes, it does. But I'm telling you right now, it is not more narrow than the black graph. And I can prove it to you. If you were to have grabbed the black graph with your hands, if I had one more stick, life would be great. Of course I don't. I got an umbrella back there, but it's too far away. All right, so I'm going to have to try to do this like this. My arm is the x-axis. Where these sticks are intersecting my x-axis are my x-intercepts. Now watch what happens as the graph gets more narrow. The x-intercepts get closer together, don't they? Now look at my red graph and my black graph. Did the x-intercepts get closer together? These 2 points did not get closer together. And that is my proof that the graph is not more narrow. The graph is taller. That's the proof. Now, what does it mean for a graph to get taller? For a graph to get taller, what that means is you put your hands on the graph at right above the x-axis and right below the x-axis, and then you did this. And you pulled every point farther away from the x-axis. But which points didn't move? Well, the x-intercepts didn't move. Why? Why is always the question. Well, here's why. F of x means y values, right? So isn't this telling me to multiply my y values by 2? That's what that says, right? And what is the y value at both of those points? The y value. When you're on the x-axis, what does y equal? 0. And what is 2 times 0? 0. So there you go. The x-intercepts do not move when a graph gets vertically stretched or shrank. And this one, because the points, all the points except for the x-intercepts, all the other points got further away from the x-axis, and the dead giveaway was, look at the vertex. This is a vertical stretch. How much taller? It is exactly twice as tall. So we would describe this as a vertical stretch factor 2. And I had another point I wanted to make. Trying to remember what it was. Oh, what is the dead giveaway that this was not a shift? The dead giveaway is that the graph changed shape. If it was a shift, the graph's shape would have been identical. And if it was a reflection, the graph would have been pointing the other direction, up or down. But because the graph physically changed shape, that is the dead giveaway that you have a stretch or shrink happening. Yes, ma'am. Emma. So what she's asking is, wouldn't multiplication always mean a stretch? No, and here's why. We don't divide with transformations. We either multiply by a whole number, which you just saw, or we multiply by a fraction. Fraction bars mean divide, remember? So we could be multiplying by a whole number like 2, which would be a stretch, or not a whole number, like 1/2. So we should be pretty obvious what's going to happen here. This one's clearly going to be a shrink. Yeah. So let's make that happen. It says, we're going to do the exact same math. It says put a 1/2 on the outside. And if we multiply the whole left side by 1/2, we had better multiply the whole right side by 1/2, making sure to capture the whole right side with a set of parentheses. And yeah, you have to distribute it to both places, both in front of the absolute value bars and to the -2 at the end. We'll call this one H. Like that. And we have to make a point tree again. Point trees are always done the same way, which is nice. And for this one, we'll actually get to demonstrate the little shortcut that I taught you on how to pick next points, which, by the way, does not have to be followed. It's just so you don't have to graph decimals. It's completely up to you. Our job is to figure out what we have to plug in on the inside. Huh? Sorry? Yeah, V is vertex. What number do I have to plug in on the inside to get an X? Or to get an X, to get a 0? Inside. 0, yeah, it's the only thing that's in there, so 0. And the number to the far right is now a -1. Now there is a fraction on the front. Now, if you don't care about graphing decimals, then ignore it. If you don't like graphing decimals, then the shortcut is this. Whatever number's on the bottom, that's how far left and right you move. So I'm going to move by 2. I'm going to go 2 to the left, and I'm going to go 2 to the right. And plug in whichever one you want. It doesn't matter. I always go to the right. So y equals 1/2 of, going to drop a 2 right there. What's this number? -1. So we're going to drop a 2 right here. And, well, that 2 is positive, so the absolute value of 2 is 2. Now, Emma, a moment ago I said that there's no such thing, for transformations we're not dividing by numbers. Instead, we're multiplying by a fraction. So when you say to somebody 1/2 times 2, sometimes that's a difficult concept. But I'm telling you, instead of saying times, say of. 1/2 of 2. Because of in math means multiply. Well, 1/2 of 2 is easy, right? So instead of dividing by things, we're going to say halves or thirds or fractions of numbers. So 1/2 times 2 is 1. This is 1 times 1, which is 0. And we will plot those 3 points. 0, -1. Ooh, the vertex moved. But the x-intercepts did not. See, for this one, come on, board, catch up. For this one, all the points got closer to the x-axis. And because all the points got closer to the x-axis, this graph did not get wider, it got shorter. Again, I'm sorry? Well, it went to the point 2, 0 and -2, 0. But that's just because I got 0 when I plugged in x equals 2. You see, the only points that didn't move were the x-intercepts because you were multiplying the y values. You were cutting the y's in half. You made this thing half as tall. So this would be described as a vertical shrink of factor 1/2. So how about that? You put a 2 on the outside, and I think this is what Emma was trying to get at. In her mind, she was multiplying by whole numbers. And she says, anytime you multiply by a whole number, wouldn't that be a stretch on the outside? I think that's what you were getting at. And yeah, it would be. So anytime you multiply by a number outside that is, I don't want to give up the rule here, somewhat like a whole number, it would be a vertical stretch. The point is, I put a 2 on the front, and this thing got twice as tall. It did exactly what we thought it would. Look at that, an outside change, a y change, once again doing exactly what we thought it would. And a 1/2 on the front, outside, y change, once again doing exactly what we thought it would. Vertical shrink, factor 1/2, because it's half as tall. So the rules, and this is what actually Emma was trying to say. So Emma, instead of saying a whole number, because technically negative numbers are whole numbers, we're not going to say that it's a vertical stretch when I multiply by a whole number. What I'm going to say is it's a vertical stretch when I multiply by a number that is bigger than 1. That's what you were getting at. Yeah, you were having trouble putting it into words, but I knew exactly what you were saying. I just didn't want to give it up yet. So yeah, when you multiply by a number that's larger than 1 on the outside, you have vertically stretched this thing. So then what makes it a vertical shrink? Matthew M? Well, I mean the rule. So it says vertical stretch if A is, this is more than 1. So he says it's a vertical shrink if A is less than 1. Now let me ask you a question, Matthew M. 0 is less than 1, right? So if I multiply the whole function by 0, do I still have an absolute value function? No. I don't. How about that? And negative numbers are less than 1, aren't they? But negative signs mean reflect. So we can't say numbers that are just less than 1. We have to be more specific. That's half of it. They have to be between 0 and 1. And again, that's what Emma was trying to get to. So a fraction that is smaller than 1, but clearly not negative. And that's because a negative sign is its own reflection. A negative sign is its own transformation. It is a reflection. So whenever you see a negative number sitting on the front, it's your job to separate those two ideas. Negative means reflect over the x-axis. And then you just ask yourself, is the number between 0 and 1? Shrink. Is the number bigger than 1? Stretch. And the words that you would use to describe it is a vertical stretch or shrink of factor and then whatever the A value was. Vertical stretch or shrink of factor, I don't know, 1/3 or something like that. Vertical shrink, factor 1/3. Vertical stretch, factor 4. Things like that. So what do you think about vertical stretching and shrinking? And remember, you're not going to have to graph these at home. It's not too bad, right? Once again, y changes, not that bad. So it's time for me to introduce a concept to you that doesn't even exist in about half of the Algebra 2 textbooks in the country. That's horizontal stretch or shrink. A lot of publishers don't even include it. But because it's hard. Oh, we're doing it. Because the state of Florida said I need to. So here we go. Horizontal stretch or shrink. I am going to do my best to make it easy. So as long as you're engaged and paying attention and asking questions, then it won't be that bad. Horizontal stretch and shrink. Same exact graph, same exact f of x. Absolute value of x, -2. What I have done is I have replaced x with a 1/2 x right here. So this is an inside change. Every time there's an inside change, your job is to open a set of parentheses everywhere there was an x. Whether or not you think it was necessary, just do it. And substitute, replace x with whatever I put in there. So I'm going to replace it with this 1/2 x. We've been asked to call that g. Yes, sir. What's the question? Yes. The x inside the absolute value bars? If it said 2x, you would do 2, and then you'd open a set of parentheses, and you'd fill it in. And then, yes, you would have multiplied the 2 and the 1/2 to simplify. Yes. Now, this time, there's nothing in front of the x. So, legitimately, we just drop the absolute value bars. Excuse me, the parentheses. They're not necessary. The absolute value bars are. They have to stay there because we don't know what x equals. And there you go. It is now time for us to make a point tree and graph this bad boy. A lot of students will get this part wrong, right here. Remember, your job is to plug in a number on the inside that gets you a 0 on the inside. So what you're going to want to do is ask yourself, 1/2 times what equals 0? 0, not 2. You'd be amazed how many students put a 2 there because they remember that 1/2 and 2 kind of cancel each other out. But you're trying to multiply to get a 0. And the y value of the vertex is found by looking to the far right. It is -2. Now, again, I taught you a trick. I said anytime there's a number on a fraction on the outside of the absolute value bars, okay. Actually, if there's a fraction in front of the x, either in or out, it doesn't matter. You don't mind graphing decimals, then plug in whatever the heck you want. If you're like me and you don't want to graph decimals, then you look at the number on the bottom of the fraction. It's a 2. And you go left and right that many. So I'm going to go left 2, and I'm going to go right 2, and I'm going to plug them in and see what we get. So this says 1/2. I'm plugging in a 2 right here, times 2, -2. Well, 1/2, instead of saying times, say of. 1/2 of 2 is 1. And that 1 is already positive, so just drop the bars, and you get -1. So throw you a -1 here and here, and plot these dots. No, don't. We haven't gotten to the difficult part yet. There we go. Remember, you're not graphing at home, okay? So let's plot these dots. 0, -2. Hey, look at that. The vertex didn't move. 2, -1. -2, -1. Connect your dots to the best of your ability. Catch up with me, panel. There it is. And this graph is G. Notice the vertex didn't move, but the x-intercepts did.
They shrunk?
Well, you're going from black to red. Red is the new one. So because the vertex didn't move, if this was black graph, you're literally grabbing this thing and you're doing this. So this graph got wider. This one did get wider because the x-intercepts were forced to move. I told you when something gets shorter or taller, the y values either get farther away from or closer to the x-axis. When a graph gets wider, you're grabbing both sides of the y-axis and you're doing this, and you're pulling that y-axis like that, imagine. So all the points, as it gets wider, will get farther away from the y-axis. And if you were shrinking it horizontally, all the points would be getting closer to the y-axis. Dead giveaway is x-intercepts. Also, it changed shape. So you knew there was some kind of stretching or shrinking going on. So you see it change shape, and you go, okay. So I'm asking, did it get wider or did it get shorter? So then what you do is you look for the x-intercepts. And you go, well, the x-intercepts, the vertex didn't move up or down, but the x-intercepts did move left or right. That was horizontal changing. So this one was actually wider. So this was a horizontal stretch. How much wider? Well, the original y-intercept was, or excuse me, x-intercept was 2. The new x-intercept is 4. What did I do to my x's? I doubled it. Oh, and he hit the nail on the head because what kind of changes do x's do? Opposite. So it looked like cut your x's in half, but we did the opposite of that. We doubled them. How about that? That is what makes it difficult for students, is the descriptions. So this next one that says f of 2x looks like you're doubling your x's. So what are you actually doing to your x's? You're actually going to be cutting them in half. And the thing is I'm only graphing this so you're not just trusting me on that. The graph is geometric proof that I'm not full of baloney, okay? So let's plug in a 2x everywhere there was an x. And once again, these parentheses, we're not serving a purpose. Absolute value bars do, but the parentheses don't. And we will just make a point tree and plug in, just like we've done every single time. So once again, you're trying to get a 0 on the inside. So what would you have to plug in to get a 0 on the inside? 0, because it's 2 times 0, not a 1/2. It's 0. Oops. Want this to be blue. 0. And the y value of the vertex is still the number to the far right, which is still -2. Huh, that vertex didn't move. It's still at 0, -2. How about that? Now there's no fraction. Feel free to move left and right by 1. And plug in whichever one you're more comfortable with. I like the one to the right. So 2 times 1, and then -2. That's absolute value of 2 minus 2, which is 2 minus 2, or 0. So my vertex didn't move, but my x-intercepts got closer together. How about that? This one's H. My x-intercepts got closer together. The vertex didn't move up or down. The graph did change shape, so you know it's a stretch or a shrink. Since the vertex didn't move up or down, it can't be a vertical change, must be horizontal. And you should have seen that the x-intercepts got closer together. This thing is more narrow. So this would be considered a horizontal shrink. It looked like right here you were doubling your x's, but what you actually did was you turned them from 2's to 1's. So you actually cut them in half. So this would be described as a horizontal shrink of factor 1/2. Once again, what's on the inside of the F rule is a liar. And that's why there are X's. Remember, they do the opposite of what we want because they're liars. The F rules lie. You know, it doesn't lie? The verbal description that never lies. If I say shrink, it doesn't matter if I'm talking vertical or horizontal. If I say shrink, I had better say a number that is between 0 and 1. If I say stretch, it doesn't matter if it's vertical or horizontal. I had better say a number that is larger than 1. The F rule for inside changes is a dirty liar, though. So this time, if I wanted to get a horizontal stretch, well, I had to use a number on the inside that was between 0 and 1. And this time it's a b in front of the x because it's on the inside. But when we put a 2 in front of the x, that was actually a shrink. So if you want a horizontal shrink, then the inside, for the F rule, the inside has to be a number that is larger than 1. So say like, the F rule does opposite. So when it looked like we were doubling our x's, no, we were cutting them in half. When it looked like we were cutting our x's in half, no, we were doubling them. What do those two numbers have? What kind of relationship do those two numbers have? 1/2 and 2. You answer me, or you're just stretching? Just stretching. Who knows a word for that? The relationship that 1/2 and 2/1 have. It's a vocabulary word.
Oh, it's what they call perpendicular.
You're thinking about perpendicular lines. Their slopes are, yes, flipped over, but they're also negative. But that's part of it. But what is the flipped over fraction called? When you flip it over, it starts with an R.
Oh, reciprocal.
There it is. Reciprocal. We use the reciprocal inside the F rule. The description does exactly what it says. So if you wanted to say horizontal shrink factor 1/2, you say it. But the F rule would say F of 2x. It uses its reciprocal. So what we say is a horizontal stretch or shrink of factor 1/b. This means the reciprocal of the description. I'm out of space. Suck it in, description. There you go. That's what this means. So the F rule does the opposite of what the reciprocal actually, of what the description actually says. The description is what the description is. The F rule is the dirty liar. And that's what's hard for the students. It's not, you don't turn it in tomorrow. You should do those 5 questions tonight, but that's only the first half of homework number 5. So you don't turn it in tomorrow. It's not due till Thursday. Nothing is due tomorrow. No. Today would have just been turned in homework number 4. So the first question says, write a function, we'll call it g, whose graph is a horizontal shrink. Okay, I see the words horizontal shrink, and I see factor of 1/3. And we're going to run through our script. Okay, class. It says horizontal. Horizontal changes. Is that x's or y's? Lots of people in. So horizontal, guys. Here.
Oh, you said horizontal.
So here you go. This one looks like the horizon. So am I changing x's or y's for horizontal? X's. So this is an x change. Do x changes happen on the inside or the outside? Lots of voices.
Inside.
X changes are inside. And are inside changes same or opposite? Opposite. Good. Good. And now, because I said stretch or shrink, I know I'm going to be using a multiplication. So I'm going to be multiplying by something we've already said on the inside. And since it's opposite, what am I going to be multiplying by? Not opposite number, opposite effect. No, that says 1/3. So it'd be 3/1. Yeah, you use the reciprocal. So you would be doing f of, 3x. Like that. And we'll call that g. And once again, these parentheses weren't necessary. And you'd be finished there. But do you see how important the script is? It's necessary. When you're doing your homework, you should be running through that script, asking yourselves those questions. See, the F rule used the opposite of what the description said. And by opposite, I mean the opposite effect. Not opposite number, opposite effect. It looks like we should be multiplying by 1/3.
But we used the reciprocal, and that's how we got 3x.
Yes. Yes. If I say horizontal stretch or shrink, you are multiplying by the reciprocal. And you're describing, like if I said, what does f of 3x tell you to do? You describe it using the reciprocal as well. And then the last one says vertical stretch. Okay, vertical stretch, factor 2. So you ask yourself, and this is what the questions you ask yourself at home. If it's a vertical change, is this x's or y's, class? Lots of people.
Y's.
Vertical change is a y change. And it is on the outside. Then you ask yourself, is that same or opposite since it's a y change? Lots of people, same or opposite for y's? Come on. Same. And since it says stretch or shrink, we know we are multiplying. And since we said same, you just multiply by 2. But you've already told me it's on the outside. So you take your f of x, and you multiply by a 2 on the outside. And you have to make sure that you have to capture the entire side. And once you distribute your 2, and rename it, of course, you are finished. And there it is, by the skin of our teeth. Thank you, everybody.